So, good afternoon. I'm going to present the paper HisTorE, Differentially Private and Robust Statistic Collection for Tor. Oh. Okay. As we all know, Tor is used by millions of people all over the world for different purposes. This is a video from TorFlow website. But all we know about Tor is the shape of the network, like how many relays are there, but we don't know for what purpose Tor is being used. Okay. So according to the Tor project, Tor is used by ordinary people for private browsing, by journalists for reporting news, and by whistleblowers for reporting wrongdoings. However, according to many others, Tor is used for malicious purposes, like recently Cloudflare reported that 94% of Tor exit traffic is malicious. However, this is subject to debate, and what we would like to do is provide strong research evidence of how Tor is being used or misused. So we would like to measure Tor. So maybe we can just capture the exit packets from Tor and then perform a packet analysis on them. However, research studies show that this is very wrong because it could endanger users' anonymity. So what we would like to do is safely measure how Tor is being used. So here, the maintainers of Tor would like to know how many exit relays forward traffic to google.com. The naive solution would be for the exit relays to keep logs of the website visits. However, research studies show that this could endanger users' anonymity, and this is antithetical to Tor's mission because Tor does not currently log client connections or website visits. Also, the measurement framework should not provide new attack surface and risk users' anonymity in some other way. So this is a sneak peek of how safe Tor measurements can be done through differential privacy. And so we have N relays over here, each of them logging client connections in the last epoch. Epoch is nothing but the duration of the measurement. So here we are assuming it to be 1 hour. And each of the relays have logged their client connections, say 21, 28, and so on. We would like to do privatized analysis on the database. So we would like to know the distribution of client connections as seen by the guards. So usually, using differential privacy, this is done by adding noise to the actual value. So we have got an output here, like the number of guards versus the number of client connections. So you can see two bars there. One is the red bar, and the other one is the blue bar. The blue bar is the noise result with differential privacy guarantees, which we will see in a moment. And the red bar are the actual values. Both the values are really close, so you can say that differential privacy provides good accuracy. So just a primer on differential privacy. So the chance that this is the result in two worlds where relay 1 submits the response or relay 1 does not submit the response is similar. So this is differential privacy guarantee. So in both the worlds, this being the result, the probability of this being the result is similar. So irrespective of whether a relay submits a response or a relay does not submit the response, the probability of this being the result is almost the same. So it minimizes and quantifies the privacy risk. It provides good accuracy. And moreover, as you can see, we have not made any assumption on the computational capability or the knowledge of the attacker. So HisTorE is not the first scheme to measure Tor as such. So previous research studies have already measured Tor like PrivEx and PrivCount, and they raise the bar for safe Tor measurements. They use differential privacy to measure Tor. So in PrivEx and PrivCount, based on them, you get that output. You get the number of client connections the number of connections to google.com. However, I would like to remind that Tor is a volunteer-operated network, so relays can behave maliciously. Let's assume there is just one malicious relay, just a single malicious relay. It could drive the value to some arbitrary value, like 100 connections. So this is by just presence of one relay. However, this is outside the threat model of PrivEx and PrivCount, but here is where HisTorE comes into picture. HisTorE addresses this attack. So now we present our scheme history, histogram query for Tor with epsilon delta differential privacy. It provides strong integrity guarantees. That is, the error that malicious relays can contribute is bounded by the number of malicious relays. And it is resistant to compulsion attacks. We will see what is compulsion attacks in a minute. And it's really highly accurate, and it incurs low overheads. So compulsion attack. Gathering statistics poses privacy risk because Tor inherently doesn't keep logs of client connections or the website visits. So if relays keeps logs, then they could be forced to reveal their logs by extra legal compulsion or through a subpoena. So here, the boss of the person who is operating the relay is forcing it to reveal all the logs or like blackmailing that he would be fired. However, relays cannot decrypt their own counters because they are like obliviously encrypted in such a way they cannot decrypt it. Previous research studies, PrivEx and ProCount, HisTorE is also resistant to compulsion attacks. So this is a really high overview of HisTorE. We have three participants, the analyst, the relays, and the mixers. Analyst, at least initially, we envision it to be the maintenance of Tor. So the analyst poses the query, like here example, how many client connections have the guard seen? And it also gives the ranges for these client connections, 0 to 19, 20 to 39, and so on. Relays are, could be guards, exits, or middle, which keep track of the static of interest, like it just keeps log of the client connections or the website visits. And they keep it in an oblivious manner, so even they cannot read it. And then there is mixers. They are third parties which add differentially private noise. So let's say there are 21 connections to the first guard, 28 connections to the second guard, and so on. These are all maintained in the oblivious counter. And then the relays obfuscate them and pass it over to the mixers. The mixers decrypt the value, but the values are still obfuscated, so the mixers don't learn anything. And then they add the noise. The noise is also obfuscated, so the mixers don't learn anything. And they send it over to the analyst. So the analyst deobfuscates the result, removes the average noise, and publishes the result. So trust assumptions. Obviously, like all these participants could be malicious. They could disobey protocols, submit false responses, or they can even refuse to participate. So here are the three participants, the mixers, the relays, and the analysts. And the mixers can be malicious. The relays can be malicious. One of the three mixers can be malicious, and the analyst can be malicious. So, a malicious mix can collude with a malicious relay. However, all that will be revealed is only the logs of the malicious relay. This is already true in case of Tor, like without HisTorE. If a relay operator wants to be malicious, he can keep logs and he can reveal them. So HisTorE gives the same guarantees. And same is true when a malicious relay colludes with a malicious analyst. However, HisTorE does not allow collusion between a malicious mix and a malicious analyst. So now let's see how relays can maintain oblivious counters. So the analyst wants to know what is the distribution of client connections as seen by the guards. So here is the graph, the number of guards versus the number of client connections. This is directly a one-to-one mapping. So there are 4 bins in the histogram. You have a binary vector of length 4. And each relay sets 1 based on the connections they have seen. Let's say the guard has seen 23 connections. So it sets second bin to 1. So at most 1 bin is set to 1. And each binary element is GM encrypted using the public key of a mix. So the relays cannot read the values inside those counters. And here we use 2 properties of the GM encryption. One, it's a probabilistic public key bit encryption scheme. And second, it's XOR homomorphic. So robustness. Let's say there are C relays, and this is the output they have got via HisTorE, the number of guards versus the number of client connections. As we have already seen, relay operators can be malicious, that is, they can report erroneous data. So let's say there are F malicious relays. However, malicious relays can only contribute 0 or 1 to a bin, because GM encryption ensures that if they submit some other value, they could be trivially detected. So at most, each relay can submit a 0 or 1 to each bin. So therefore, the total error is bounded by the number of malicious relays. And this is the major advantage of HisTorE over previous research studies. So far we have seen how relays maintain oblivious counters. Now let's see how relays increment their oblivious counters. So this is the bin here, like the bins 0 to 2, 3 to 5, and so on. And the relays initialize them to GM encryptions of 0, all but the first element, which they initialize to 1. And they also initialize a low order counter t equal to 0. And whenever the relay observes the static of interest, that is here say the number of client connection, like a new client, it increments the low order counter. So it sees a new packet, it increments the counter. It sees a new packet, it increments the counter. It sees a new packet, it increments the counter. And now t equal to 3, which is equal to the bin width here. So at this point of time, the relays just right shift their counters. And then they reset the low order counter t equal to 0. So this is how relays can obliviously increment the counter, so they don't learn anything inside of the counter. So now coming back to compulsion attacks, relay can be forced to reveal their counters. As you can see, oblivious counters minimize the information that a relay could leak. Everything is GM encrypted using the public key of a mix, so they cannot reveal it. All they could reveal is the low order counter t, which is the least significant bits of the counter, like least significant bits of the number of client connections. So now let's see, like the analyst poses a question like how many client connections have the guard seen? It gives a series of ranges. So far what we have seen is how relays can maintain oblivious counter, how they can increment oblivious counter. Now we are going to focus on how relays obfuscate their counter. So the analyst issues the query and it gives 5 bins. For this example, we consider 4 relays. Each of the relays maintain 3 redundant copies of the oblivious counter. Each counter is encrypted with the public key of a mix. And let's say these like 21 client connects to relay 1, 28 to relay 2, and so on. Accordingly, they set their oblivious counter. So here we see that all the 3 relays, like the relay 1, 2, 3, set their second bin to 1, and the last one set its third bin to 1. And then they obfuscate it and send it over to the mix. So far we have seen how analysts post the query and relays maintain oblivious counter, increment them, obfuscate it, and send it over to the mixers. Now let's see how mix will add differentially private noise to them and forward it to the analyst. So here mixers receive all the responses R1, R2, from R2, R3, and R4. They decrypt it, but still the values are obfuscated, so the mixers don't learn anything. And then we add noise based on Chen-Natal scheme. And here the mixers don't learn the noise as well because the noise is also obfuscated. And then the mixers shuffle them column-wise. Once the mixers have shuffled them column-wise, they just forward it to the analyst. Here we just consider 1 mix because the mixers are just for redundant purposes. So all the 3 mixers perform similar operations. The analyst deobfuscates the result it has obtained, and then it aggregates it, that is, it sums the columns of all of them, and then it removes the average noise. Here we added 3 noise vectors, and then it publishes the result. So as you can see, the result is 0, 2, 0, 0, 0. This is really close to the actual value, which was 0, 3, 1, 0, 0. And now we are evaluating HisTorE. Like, let's just consider the query, how many client connections have the guard seen? There are other kinds of query in the paper. So from TOR Compass website, we take the number of guards and the guard selection probability. From TOR metrics, we take the number of direct users, and then we assign client connections to the relays. Again, the details are in the paper. So we assign 21 connections to relay 1, 28 to relay 2, and so on. And based on this simulation, we run all our experiments. So now accuracy, the number of client connections as seen by the guards. So you can see we have obtained a graph of the number of guards versus number of client connections. The red bars are the actual value, and the blue bars are the noised value obtained via history. Both of them are really close. We also measured how close they are using two distance metrics, the R-square and the Bhattacharya value. The R-square distance, if it is close to 1, and if the Bhattacharya distance, if it is close to 0, then the two distributions are similar. And we also performed other experiments like guard bandwidth and exit bandwidth, and we got similar good results for them as well. Now let's see the communication cost incurred by history. We plotted a graph by varying the number of bins in the histogram. In a real world scenario, we assume the average number of bins to be 80. And for 80 bin, the mixes incur a cost of 95 megabytes at most. And the analyst incurs 6 megabytes at most. And the relays just incur 151 kilobyte. So this is roughly 42 bytes per second for each relay every epoch. So an epoch is R long. This is very minimal. And summary, histogram query for TOR with epsilon delta differential privacy. It provides strong integrity guarantees, that is the maximum influence by malicious relays is bounded by the number of malicious relays. It provides strong privacy guarantees, that is it's resistant to compulsion attacks. It's highly accurate, and it incurs low overheads. Thank you.
We have time for a few questions.